forgot to record. Okay, awesome. So this is a video reference for when it comes time to the test. It's about the statistics class and its application to engineering. I think it's mainly statistics. I wanted to make this video for me, mainly to help me study. However, I said, well, whatever I'm studying, I think free information and free education never hurts the public. So I hope my notes can either help other students, can help younger students who want to learn a little bit more about statistics, or people who do not have the money and the access to be able to take classes about statistics. Okay, without further ado, we'll be talking about sample spaces and events. It's broken down into 3 sections. This is the objectives that I had over the whole chapter, but we'll cover maybe those in later videos. At least we'll be able to cover 1 and 2 to some extent. So, why do we care about statistics and probability in the first place? Good question. The best I can summarize it is in real life, because they always give you experiments, but just like experiments in real life, no matter how carefully implemented you have a routine, there's always random components within it. Many times those components are insignificant and they don't really make a difference, so we don't like to focus on them, we don't mind. But sometimes those little components or some random components can affect the outcome of whatever's happening in our lives in non-obvious ways. For example, who knows, maybe there is a chance that a hurricane hits and that of course affects the life that you will be having during that day. Okay, so due to that, it's important that we learn how to analyze and model data from our experimental data to be able to look at our results and make better conclusions about them, to be able to determine if something's true, something's not, if it's within a reasonable range. It allows us to build so many more tools and ways to see things and outcomes to help us make better, let's call them conclusions about what we see. And those conclusions, we use them to also make better decisions because we make decisions of conclusions. So, statistics and the probability, but mainly statistics, help us interpret these results to avoid invalidation of them due to the variations, those pesky random events. So what is the relationship between probabilities and statistics? I'll draw a diagram here from a bigger population to a smaller sample. Probability is technically the basis for statistics. Without probability, there probably is no statistics. It helps us talk about samples, etc. However, statistics helps us do 2 things. They can describe the sample that we took it from, and they can help us better organize it and better understand it, but they can also help us make inferences and guesses, we can say, but not guesses merely, inferences and I would say predictions about a bigger population, and that's really, really useful. So, let's talk about, variability and an example where this would apply. So we all know Ohm's law, I equals VR. It's pretty well modeled. However, here we have a measurement. Now, there's some theoretical, we made an experiment in our head, and each discrete point is a measurement. Now, this line is supposed to be the theoretical value, but as we can see, there's some variation in our system such that the points are not exactly the theoretical value predicted. And later on, we'll be able to study these and determine, well, from now we can see it's pretty valid, it follows a trend, but determine if it's a valid conclusions we're making from this, if it's a valid results that we're getting from this experiment, if it's well designed, we can get more feedback on it. It's really, really useful for that. So let's talk about some terminology. In pink, I have terminology that I believe is important to remember. Random experiment is technically an experiment that can have different outcomes if we implement it the same way. And that happens a lot. There's a lot of unknowns that we don't know, even in the things that we try to implement the best way. Let's talk about some other statistics lingo. Sample space is a set of possible outcomes of a random experiment. And usually we express it with a S. So you'll see it like that sometimes in some notation, but it's usually expressed like that. It's the set of possible outcomes. So for example, if you have 2 shots of a coin toss, then you have your sample space would be like heads heads, heads tails, tails heads, tails tails. So let's talk about type of data. Discrete data is the one that consists of a finite set of points or finite outcomes, like 1, 3, 4, 5. And continuous data doesn't matter if it's finite or non-finite, as long as it contains an interval of real numbers that it suggests continuous, then we can consider that continuous. Here are some examples. So for example, here we imagine resolution to be, I wrote this wrong, right? This would be finite. because it's sort of like a 1 and 0 type of thing. Yes, no, maybe that would also be finite. This is discrete, pardon. Discrete obviously is finite. Now here we have continuous. Why is it continuous? Well, the resolution just says that x has to be greater than some amount 0. So it's a range of values. It contains an interval, right? So it's continuous. So let's talk about ways we can model these. Tree diagrams. You've probably seen these. You start at one single event, and you move down to events and to all the possible probabilities and possibilities. We talk about a coin toss with 2 tosses, so 1 toss, 2 toss. And at the end, you can count up all these and determine your likely events. There's also other ways to do it, such as multiplication rule, where you can say you have first toss, second toss, you multiply the number of possible outcomes, and then you have 4 outcomes. It's just the same thing, different ways of arriving at the same answer. So let's talk about more lingo. Events. We talked about possibility spaces. We talked about sample spaces. Well, events are just a subset of the sample space, so like a part within the sample space. What can we see here? Well, we see different things, such as union notation. Union looks like a U. It usually unites 2 sets. What does this mean? It's sort of like an OR statement in coding. It means all the sets of E. So if E is like 0 to 5, E1, and E2 is, let's see, 4 to 8, then the union would be 0 to 8 because it includes all the values of E and all the values of 2, and obviously everything within. We'll talk about intersection. Intersection looks like a little backwards U or a horse hoof. Well, intersection is not too difficult. It's just the elements that both E1 and E2 share. So if E1 is 0 to 5 and E2 is 4 to 8, well, the only element that they share is 4, right? 4 and probably 5, 4 and 5. These are the only 2 that they share. So let's talk about complements, and that would be the intersection. Let's talk about complements. Complements are usually seen in either one of these 2 ways. Some set to the C or some set in the apostrophe, which looks like a prime. It just technically means the set of all elements in the sample space that are not in that event, an E event. Another way you can say it is everything that is not this event, that is in the sample space. So we'll talk about, and as you can see, a lot of this lingo is not too detached from normal lingo. It's easy to understand, it's intuitive. Like a mutually exclusive clause, well, there's mutually exclusive events. That pretty much means that they have nothing in the middle, right? So then we can logically follow that the intersection between them, or whatever they would share in the middle, has to be 0, or an empty or a null set. And we can also determine then, due to this, that if the complement means all the values that are not that, then the complement of a complemented set is just going to be the set itself. It's sort of like saying, I would not elements that both E1 and E2 share. So if E1 is 0 to 5 and E2 is 4 to 8, well, the only element that they share is 4, right? 4 and probably 5, 4 and 5. These are the only 2 that they share. So let's talk about complements, and that would be the intersection. Looks like a prime. It just technically means the set of all elements in the sample space that are not in that event, an E event. And as you can see, a lot of this lingo is not too detached from normal lingo. It's easy to understand, it's intuitive. Like a mutually exclusive clause, well, there's mutually exclusive events. That pretty much means that they have nothing in the middle, right? So then we can logically follow that the intersection between them, or whatever they would share in the middle, has to be 0, or an empty or a null set. And we can also determine, means all the values that are not that, then the complement of a complemented set is just going to be the set itself. It's sort of like saying, I would not do that. It's like a double negative, right? They cancel out. So let's talk about different ways we can go around this, because these simplify the life. Conclusions that we can make. Let's follow the distributive law first. We have A in union with a B, and it's both of them, like the whole A in union with a B is an intersection with a D, then we can logically make out that A in intersection with a D is in union with all the values that are B in intersection with a D. It's sort of like a mathematic, take this, multiply it by each, we will eventually end up with this. Also, as a product of the De Morgan's law, that is not necessarily explicitly stated here, but it implies that in parentheses, let's say you have all the sets of A in union with a B and all the primes, so technically all the values that A shares with B, not that. So not all the values that A shares with B, well, that technically is not all the values with A and not all the values with B. This is why we can make such logical conclusion. And so the intersection of the complement of A and the complement of B is the same thing as we could say, if we had been under parentheses, the union of A and B, whatever the complement would be of that. And let's never forget a reflective property. If A is in union with B, B is in union with A. It's really simple. It shouldn't be that big of an issue. Some people forget. One of the most important things that helps us, or at least helps me, future me reference, maybe hopefully won't be that different, is also just draw Venn diagrams. And this is like a really good, not only to help us determine, like, as we draw up here in the top, but it's like, especially with the reflective property. Call this A, call this B. Like, it's the shared values in between. It doesn't matter the order. Okay, this is where we stop for now. Hopefully it was not a really crappy lesson or a really crappy review video. I will try to make them better. This is my first one. But I hope this is useful for me in the future, or for anyone else watching it who might need an introduction or wants to learn about statistics with me. All right, whoever's watching, thank you. And give a like, comment if you want, it doesn't matter. Share it for like carefree education. As long as we're making the world a better place, it's better. All right, bye-bye.